Airfoils are incredible objects. They produce so much lift for very little drag penalty. As such, they are found on so many different applications from airplanes to cars to wind turbines. But in all these applications, they usually exist at a uniform temperature. And to change an airfoil's performance, instead of changing the actual surface temperature, we usually focus on just changing its geometry, whether that's making it thicker so that its lift and stall characteristics change, or cambering the airfoil so that produces more lift at low angles of attack. But what would happen if you do change the airfoil's temperature? Would that even do anything? What would the effects be? Would they be favorable? And that is what we're looking at today. And to do that, we're looking at this paper called Improvement of Airfoil's Aerodynamic Efficiency by Thermal Camber Phenomenon at Low Reynolds Numbers. It is open access, you can find the link below. Now, heating airfoils isn't a new phenomenon actually. In fact, any airfoil that breaks the sound barrier is going to experience heating to some extent because of the shockwave that forms over it. But in that case, usually the heating is just a side effect of the unwanted shockwave, and we rarely want that heating anyway, so it certainly isn't deliberate. What's more, the heating is highly dependent on where the shock forms, so you are kind of limited as to where you get the heating to occur because you usually alter the airfoil to mitigate the shock. Hence, the heating is a secondary concern. But in this paper, the researchers deliberately heated different parts of the airfoil to see how that affected the performance. And now initially the question is, why? Out of all the things you could do to an airfoil, why heat it? What is the logic behind it? Well, these researchers say that there is one particular application that could benefit very much from heating, and that is micro air vehicles, so MAVs. So MAVs are great because they operate at very low Reynolds numbers because they are small and don't fly very fast. Hence, they are highly susceptible to stalling. This stall occurs because the boundary layer is usually very laminar, and hence it doesn't have enough energy to resist the adverse pressure gradient that forms over the airfoil. So it separates, and the MAV loses a lot of lift very suddenly. So the idea of using heating to manipulate the boundary layer, and other studies have looked into this, but they have primarily focused on symmetrical airfoils, so ones that don't have any camber. And generally, they found that cooling the surface reduced the drag of these symmetrical airfoils and didn't change the lift too much. So in that particular case, if you wanted to improve a symmetrical airfoil's efficiency, so its lift to drag ratio, you could do that by cooling the airfoil. It then becomes a question of whether the energy you use to cool the airfoil is lower than the energy you would save from the positive aerodynamic benefits or not. If you have to use more energy than you save, then it isn't good for flight in general. It's not as efficient. So these researchers wanted to investigate the effects of what they called thermal camber on an airfoil's performance. Now, the authors don't give a specific term here in this paper what thermal camber is, but from the context and from seeing what they use the term throughout the paper for, thermal camber is where you heat the upper surface and lower surface of an airfoil by different amounts, so you effectively introduce this pseudo camber through heating. As such, the flow goes over one surface and it will have slightly different properties than the other surface due to the different temperatures. So to find out whether this thermal camber approach is beneficial to airfoils, they tested symmetrical and cambered airfoils, so airfoils with and without thermal camber as well. That way, they could see first of all if there are any differences between airfoils with different geometric cambers, and also to see if a symmetrical airfoil with thermal camber could perform as well or even better than an airfoil with geometric camber and no thermal camber. So I'm really looking forward to these results because it seems quite cool. But first, let's see whether the results are accurate or not, and let's go through their setup. So they did a CFD to investigate this research, which makes sense because trying to control thermal aspects of an airfoil in real life is quite challenging. There are various problems that can arise and you need to temperature control facilities as well as make sure that the airfoil is heating in the pattern you want. So using CFD makes a lot of sense from a practical point of view. And they used OpenFOAM in RANS, which if you want to learn how to use OpenFOAM, which is a really powerful CFD software as you'll see, but it's hard to learn, then check out our courses in the link below. So to give you an idea as to how sensitive air properties are to temperatures, in equations 1, 2, and 3 here, we see various properties, how they change with temperature. And this is not an exhaustive list either. So for example, they do have even the thermal conductivity, that depends on the temperature, as does the viscosity and the specific heats. But so does density, enthalpy, and so on. So by heating the air, you stand a really good chance, from a theoretical point of view at least, of altering the flow physics over the airfoil and the airfoil's subsequent performance. Now in figure 2, we see their mesh setup, and they use a good C mesh, which has a curved inlet just here. And that helps when changing the angle of attack because you don't have to remesh everything. You can just change the inlet flow angle. They also have a good refinement region around the airfoil's nose and in the wake, which is quite good. And in figure 3, we see the size of their domain. And they've left good spacings upstream, downstream, and top and bottom. In addition to that, they did a mesh-independent study. Now, I've talked quite often about mesh-independent studies, and sometimes I get some of you amigos asking about what they are and why you need to do them. So just quickly, I'll cover them here. If you want to know what it is, or if you don't know what it is, stay tuned. If you know what it is, maybe skip ahead 2 minutes or so. So a mesh-independent study is there to determine if the results you get from your CFD are being affected by your mesh or not. Ideally, they aren't, because if they are, then that means that your results are really a reflection of real life. They're not, but rather real life plus errors from your CFD mapped onto that. So why would you get errors from your mesh? Well, assuming that your cells are good quality to begin with, so there's little skewness, good orthogonality, good aspect ratios, good inflation layers in the boundary layer, and so on, then we are left with the size of the cells. The size really matters across all different formats of Navier-Stokes CFD, from RANS to LES to DNS, and even DAS as well. The size of the cells really determine how well you're resolving the energy of the flow and the flow physics. So for example, let's say you have a vortex, but it's very small. It's so small that one cell engulfs it. Well, that means that you can't resolve it because you can't really know that it's there. As such, that flow feature, and just importantly, the energy that it contains, is now lost to you. The question becomes then, is that flow feature important to the simulation or not? Some features will dramatically change your simulation's results, while others won't. That is where the mesh-independent study comes into it. We want to start with a certain size of the mesh and then change the number of cells we have in it, thereby making the cells larger or smaller. And we'll then see the effects of that on the quantities that we're interested in. For example, let's say for this simulation, we're interested in the drag coefficient, which is actually what these researchers are interested in. So the drag coefficient is what we will concentrate on when we change the mesh to make the cells larger or smaller, and then see if that changed the drag coefficient or not. We need to also have thresholds in mind as to what the level of change that we can accept, really. So for example, if the drag coefficient changes by 5% between the meshes, is that okay? Or should it be less than 1%? And this value largely depends on how accurate the rest of your simulation is and the resources available. So if your simulation isn't very accurate to begin with, then there's no need to throw even more resources at it with this mesh-independent study and get very fine, like a converged solution here, because you're going to lose that goodness in your bad CFD anyway. And this last point, the resources available, is often overlooked by many. So in fact, the resources you have to spend are a major constraint, because like I remember having this conversation with quite a few researchers, and more inexperienced researchers will often want things to be 100% accurate. Like they want things to be just perfect. But if they were to do a measurement study, and if the drag coefficient changed by 0.1%, then for them that's too much, and you got to use even more cells. That is nice in theory, but usually you can't do that. And if you do that, then you overextend yourself in your resources used. The rest of the simulations can't be done then, because you don't have enough time, money, and or computational resources. So you can't just use all the resources possible to get the finest mesh possible and not have to worry about any errors. It doesn't work like that. It's kind of like when you go to buy your first car. You want something really special, like a new yellow Corvette with red interior. So you go to the dealership and get excited seeing all the nice cars there, then get led to the Corvette you like. It's really nice, and you're getting ready to hop in until you see the price. Then you think, well, maybe it doesn't need to be a yellow one with red interior. So you go for a pastel blue one, but still the price is way too high. And over time, your expectations on what you can afford drop more and more until you're happy just to get something with 4 wheels and a steering wheel. Doing CFD and research in general is often like that. So you can't just spend all resources on getting something completely perfect. It's really a balancing act. So bringing this all back to the mesh-independent study, these researchers in figure 3 down here, figure 4, show the results of changing the number of cells in their mesh, and hence the subsequent fineness of the mesh and its effects on the drag coefficient. Let me zoom in a little bit here. There we go. And This is for the drag coefficient of a NACA 0012 airfoil at a Reynolds number of 3000, and this is for temperatures ranging from 300 Kelvin to 400 Kelvin. So the results are really nice. We can see that as the mesh approaches 18,000 cells, here this line, this solid line here, the results start to converge, and going above 25,000 cells makes very little difference, it seems. Like above 18,000, it converges quite nicely. So the authors decided to go with 18,000 cells. Now, looking at this graph, one thing that might jump out to you is that the third finest mesh is only 6,000 cells, and the second finest mesh is 18,000 cells. So that's a huge jump. But then going from the second finest mesh to the finest, we now only go from 18,000 cells to 25,000 cells, which is a much smaller jump percentage-wise. It goes from 3 times as much to about 40% more. As such, you would expect much more than the 6,000 cell mesh should have a much greater drag coefficient change when you go to the next step, because you're increasing the cells so much more, while just by the virtue of the fact that the finest mesh isn't nearly as great a step up in fineness, that will naturally result in a smaller difference in the drag coefficient. So you might think that it kind of skews things visually, and that is true normally. But for this particular CFD, I think here it's okay, this jump still, because it's 2D, by the way. So that means that going from 18,000 cells to 25,000 cells is still a 40% increase in 2 dimensions. That's still pretty decent. That's quite a big jump still. So that jump, I think, is fine. One really nice thing about this graph as well is it shows how the mesh is independent across the temperature range as well. That's a nice touch because they are looking at different temperatures. But one thing that I would like to know is the exact angle of attack of this mesh independent study, because I can't quite seem to find it in the preamble to it. I'm just interested because it would help me understand how much the flow would be separating, and hence how important various features would be, and if they need to be considered in the mesh independent study or not in terms of the flow physics. But while I can't find the angle of attack given how low the drag coefficients are here, and as we'll see later in this paper, the drag coefficient is quite accurate, I think this angle of attack is about 0 degrees. Maybe it's 0.1 or something, I don't know. So I think that the flow physics isn't that important to consider here. I mean, it would be nice, but it isn't that important because it would be well behaved anyway. So I think overall, we can say that pretty much this mesh is independent here at 18,000 cells. Let's move on to the validation study. So in table 1, we again see the validation conditions, and again, I can't see the angle of attack. I'm guessing it's 0 degrees still. Anyway, the Reynolds number is only 3000, and which at this level, the airfoil will store at like 7 degrees, so really low. In figure 5, we see the results from the CFD and from literature. Let me zoom in a little bit here as well. Here we go. And the results look fantastic. There are almost no differences between the CFD and the literature, and that goes across the temperature range as well, from 300 Kelvin to 400 Kelvin. So we can say here that the CFD is well validated. So overall, from what these researchers want to use the CFD for, I would have to say that their CFD is like a 9 out of 10, maybe a little bit higher. There are only very minor things they could do, like look at the flow field or test another airfoil with geometric camber. But as it stands, I think we can trust the results both in the trends and the values. So let's move on to the results. Now in figure 6, we see, let me zoom in as well here, we see the effects of heating or cooling the entire airfoil. So the upper and lower surfaces are the same temperature, and they range from 200 Kelvin to 400 Kelvin, and the y-axis gives the drag coefficient. It is clear that as the temperature increases, the drag coefficient increases, and not by a negligible amount either. I mean, at 200 Kelvin, which is pretty nippy, the drag coefficient of the NACA 0012 airfoil at a Reynolds number of 3000 is about 0.0625, which is pretty good. Then increasing the temperature to 400 Kelvin, the drag coefficient is about 0.072. So about a 15% increase just by increasing the temperature. That's quite a lot. And the researchers say that at least one reason why this increase occurs is because the dynamic viscosity increases quite a lot over this temperature range too. Now in figure 7, we can now tell that this airfoil is at 0 degrees, and when the entire airfoil is heated by the same amount, the velocity distribution over the airfoil is symmetrical on top and bottom, as you'd expect. And likewise in figure 8, this shows the pressure coefficient distribution, and it's symmetrical about the airfoil as well. That makes sense because it is symmetrical and it's at 0 degrees. So the lift coefficient should be 0 as well. But what happens now when you heat one surface to one temperature and the other surface to another temperature? Well, in figure 11, we see exactly that. So we have the NACA 0012 airfoil at 0 degrees. As we'll see in a second, it's quite surprising the results, but it is at 0 degrees. And the Reynolds number is at 3000. It has its upper surface at 200 Kelvin and its lower surface at 400 Kelvin, as the legend says here. Now, the y-axis is the pressure coefficient. And if you don't know about what the pressure coefficient is, then check out a video on our YouTube channel called Aero Fundamentals number 12, Pressure Coefficient Explained. And in this figure, we can see that there is definitely a difference in the pressure coefficient distribution along the airfoil's upper surface, so this dashed line and this dashed line. And that means that the airfoil is no longer not producing lift. There is a difference there, hence there is some sort of lift or maybe downforce being produced. And this is in contrast to the black line, which is the exact same airfoil, but with no heating. So the top surface and the lower surface are both at the same temperature. And as a result, there is no lift being produced because the upper surface and lower surface have the exact same pressure coefficient distribution. So right there is proof that differential heating, which the authors refer to as thermal camber, works in making a symmetrical airfoil like a cambered airfoil. Now in figure 10, if we go up, we see a little more information about the pressure distribution around this thermally cambered airfoil. And you can see that the top surface, which has a lower temperature, also has lower pressure coefficients along it as well, which means that the airfoil is producing positive lift, it's upwards. And if you want to make the airfoil produce lift, and the top surface should then be cooler than the bottom surface, you can literally keep it at 0 degrees and just change the temperatures on the surface and you'll generate lift. That's pretty amazing. And that is for a symmetrical airfoil, by the way. Now let's look at the cambered one. Now in table 3, the data there given down here in table 3 is a bit of a shambles. I'm not sure if the PDF just rendered it weird or if they're just typos, but the authors provide some words that we can go on anyway in these paragraphs. Literally, they say that the NACA 0012 airfoil, so the symmetrical one, can produce about the same lift coefficient as the NACA 4412 airfoil when it isn't when it's thermally cambered compared to the NACA 4412, which isn't. So if you have a symmetrical airfoil, you thermally camber it. The cambered one, you don't. They can generate about the same kind of lift coefficient. So in other words, the thermal camber works really well. And the thermally cambered NACA 0012 has less drag than the regular NACA 4412 airfoil. So moving on to solely cambered airfoils, in figure 15, down here, let me zoom in a little bit, we see the NACA 2412 airfoil, which has about half the camber of the NACA 4412, but is equal in all other ways. And we see the lift and drag coefficients when you thermally, when you change the temperature of the entire airfoil. So there's no thermal camber, it's just the entire airfoil is being changed in temperature. So heating the airfoil increases the drag coefficient while severely reducing the lift coefficient. It's really bad. I mean, going from 200 Kelvin to 400 Kelvin, the lift coefficient drops by about a third. And similar trends occur in figure 16, which shows the lift drag coefficients of NACA 4412s. And this is again at 0 degree angle attacks. And no thermal camber, it's just the entire airfoil is changing altogether. Hence, here the drag coefficient increases with increasing temperature, so this blue line, while the lift coefficient again plummets by more than a third, I guess, here. So that's pretty bad when you increase the temperature. But on the other hand, if you wanted to make the airfoil better, you could always cool it. So looking at the drag ratios of these two airfoils, they're given in figure 17. They both show that increasing the temperature dramatically drops the lift to drag ratio. So for example, for the NACA 2412, actually, the blue line, at 200 degrees Kelvin, the lift to drag ratio is about 0.8, while at 400 degrees Kelvin, it's about 0.4, so like half. So increasing the temperature by double effectively halves the lift to drag ratio of the NACA 2412. And a similar kind of drop occurs for the NACA 4412 too. So again, that's good in the sense that if you can cool your airfoil completely, then you'll increase your lift to drag ratio, but the opposite is true too. So in table 4, we see the effects of thermally cambering these two airfoils that are already quite cambered geometrically. Looking at the top 3 rows, we see how thermally cambering the NACA 2412 more and more affects the airfoil performance. So zooming in just a touch here, here we go. So first of all, the more you thermally camber the airfoil, so no thermal camber, a little bit more thermal camber, the lower the drag coefficient goes, which is a good thing. And equally good is that the lift coefficient dramatically increases as well. I mean, looking at the entire airfoil, when it's just 300 Kelvin, the lift coefficient is about 0.0425, which is okay. But when you drop the upper surface to 200 Kelvin and jack the lower surface up to 400 Kelvin, so this line here, the lift coefficient goes up to 0.1227, so almost 3 times as high. That's incredible. And coupling that with the drag coefficient drop, the lift to drag ratio is about 3 times as high. So the airfoil has become 3 times as aerodynamically efficient with this thermal camber. We see pretty much the same trend for the NACA 4412 airfoil for these lower 2 rows here, where thermally cambering the airfoil by the same amount, so 200 Kelvin on the lower surface, on the upper surface, 400 Kelvin on the lower surface, results in a doubling of the lift coefficient, a little drop in the drag coefficient, and about twice the lift to drag ratio. So that's pretty awesome. The results tell us a couple things here now. First is that cambered wings, geometrically cambered wings, also benefit from thermally cambered wings too. So this idea isn't just limited to symmetrical airfoils. The second thing is that it seems like the less cambered airfoil, so the NACA 2412, benefited more from the exact same thermal cambering than the NACA 4412. I suspect that perhaps there is probably a non-dimensional way, like a way to non-dimensionalize the amount of thermal camber there is based on the airfoil's geometric camber. That way you can better compare the airfoil's performance. Like, maybe if you could kind of quantify how much thermally cambering this airfoil would change its geometric airfoil camber, like pseudo, and then you can find some kind of relationship there in the temperature. Either way, looking at it from an absolute point of view, thermal camber seems to yield greater benefits for less geometrically cambered airfoils. But either way, this research shows that differentially heating the upper and lower surfaces greatly affects an airfoil's performance, and in a good way. And with that, we come to the end of this podcast. If you liked it, hit the like and subscribe button. And if you want to learn how to use OpenFOAM, which is a very powerful CFD software but hard to learn, take our courses linked below. We go through from the very basics all the way to very advanced meshing like dynamically morphing and overset meshes. And if you're doing experimental research, did you know that you probably have a 2 to 4% error in your data and you don't even know about it? That's because the atmospheric conditions constantly change. In that Atmospheric link below, we go through the math of it as to why and how to fix it. So we'll see you next one. Peace out, amigos.